Good morning. So today we are going to start chapter 4, which has to do with exponential growth, exponential decay, and then we will do the inverses of that in the second half of the chapter, which is logarithms. So we're going to start out talking about exponential growth. So our objective is to graph exponential growth functions and then to use exponential growth functions to model some real-life situations. So an exponential function involves the expression b raised to the x power, where the base, b, is a positive number greater than 1. So when you take a number and you raise it to a power and you want it to get bigger, that original number, that base number, has to be greater than 1. If that base number is just 1, then it's not going to do anything because 1 raised to any power just remains 1, so it won't grow, it'll just stay the same. If that b value is less than 1, then it will actually get smaller. So if you think about when you take a fraction like 1/2 and you raise it to the second power, you actually get 1/4, which is smaller. So that's what we will deal with in tomorrow's lesson, which is exponential decay. So today we're going to focus on when that number that's being raised to the power is greater than 1. Positive number greater than 1, which is what's going to make the outcome grow, and that's why it's called exponential growth. So an example of an exponential function is y equals 2 to the x power. So if we were doing a problem like this, of course you can use your calculator, so you can type this into your graphing calculator and get the chart that way. That's going to be the easiest way to do that, or the quickest way. So if you go to your y equals and you just type in 2 raised to the x power like that, and then you go to your table, you'll be able to fill in, any numbers on your table there. So that's what you can do. And then when you press graph, you'll get the visual of the graph that we're about to put on our paper. Okay, so as we just saw on the calculator, and hopefully you're putting that in your calculator, we know that 2 to the negative 1/3 power is 1/8. It gives you the decimal on the calculator. That is the fraction version. Now, if you think about this, when we went back to an exponent chapter, I believe we did that in chapter 2. If you add 2 to the negative 1/3 power, remember we can't have negative exponents, so you would have had to flip that around to 1/2 to the third power, and then 2 to the third is 8. So that's where that fraction comes from. So if you were doing 2 to the negative 2 power, then you'd have 1/2 squared, which is 1/4. And then you'd get 1/2 for the negative 2. Now, anything raised to the 0 power is always going to be 1. And of course, 2 to the first is 2, 2 to the second is 4, and 2 to the third is 8. So now when we go to plot those points, just like we would normally plot any other ordered pairs on our graph, negative 3 and 1/8 is going to be estimated just above that x-axis. Then negative 2 1/4 would be like a teeny bit higher. Negative 1 and 1/2, 0, 1, 1, 2, 2, 4, and then 3, 8. So you can see kind of how that curve, those points start out very close to the x-axis, and then they get farther and farther away from the x-axis as you go from left to right. So as x approaches infinity, so as you read your graph from left to right, what's happening? Your y value is approaching infinity because it's going upward in an exponential fashion. As x approaches negative infinity, so that would be going to the left. If you remember when we talked about, the end behavior back in the polynomial chapter, as our graph goes to the left, our y values are approaching 0. So if you go back to the graphing calculator and you go to your table, you can kind of get a little bit better of a view of this. If you scroll up, as those x values go towards negative infinity or get more negative, you'll notice that the y values are getting increasingly smaller, and so much so that they're going into scientific notation on your chart there. And then when you look at the graph, you can kind of see that the graph is getting closer and closer to that x axis, but it's never actually going negative. So it's never actually crossing it. It's just kind of like lining up with it. So when a graph does that and it sort of approaches something, but it never actually intersects it or gets to it, we call it an asymptote. So an asymptote is a line that a graph will get very, very close to, but never actually touch it or intersect it. So the line y equals 0, which is actually, in this case, your x-axis, is an asymptote of this particular graph. So like I said, an asymptote is a line that a graph approaches but won't never actually reach. An exponential function, y equals a times b to the x power, where a has to be greater than 0, can model either growth or decay. And as we said, it's really that b value that's going to make the difference, because that is what's getting raised to the power. So if that b value is greater than 1, then this b value is called a growth factor, because when you raise a number greater than 1 to an exponent, the number will grow. That's why it's called a growth factor. But when that value is something less than 1 but still positive, then that number in there will be called a decay factor, because it will make the actual original number decrease. And the original number that you're starting with, like the amount of money or the amount of people or whatever the problem is referring to, that's that a value. And then that b value is called your growth factor or your decay factor, depending on what kind of number it is. And it's usually based off of some kind of a percentage or something like that. Okay, so focusing on the exponential growth functions today, we're going to be focusing on when a is greater than 0, so it has to be positive. So the way I kind of always talk about that is, well, if a is representing what you're starting with, how much money you're starting with, how many people you're starting with, in biology, maybe how many cells are you starting with, you can't start with nothing or negative something and have something happen. So for example, you cannot invest a negative amount of money and expect it to do anything, or you can't have a negative population or even a 0 population and expect anything to happen. So the a value would have to be greater than 0 for either exponential growth or decay. Nothing can happen if you start with nothing or you start with negative, which is not actually possible. So the b value can be greater than 1 or less than 1, but still has to be positive. And that's going to tell you what's going to happen with that starting value. Is it going to increase or decrease? So again, this is one of those problems where I like, kind of similar to in chapter 7 when we were talking about the geometric sequences. It's very similar actually, if you think about it. This b value, I like to put it in parentheses so that I remember that I'm only raising that number to the exponent, and then that will get multiplied to that initial amount. It's a very common mistake for people to multiply the a and the b together and then raise it to a power, which would not be following the order of operations, but it is a common mistake, I think, when the parentheses are not there, so I like to put the parentheses there. So a few characteristics of an exponential function is that it's going to pass through the point 0, a. So that y-intercept will be that starting amount. So if you think about it, we're really always going to be, for the most part, if it's a real life example, we're going to be graphing this in that first quadrant, which is that positive quadrant, right? Because like I said, if you're starting out with, let's say, a certain amount of money, it's positive. So it has to be in this quadrant. So whatever that initial amount is, like, because this is usually going to be represented by time, your x will be your time, so you can't start out in negative time either. So if you're going to start out somewhere at time 0, what's the amount of money you're starting with, or what is the population you're starting with, or whatever it happens to be, that a value will be your starting point. So that'll be your y-intercept. The x-axis will be the asymptote of the graph. The domain is all real numbers, so you can input anything you want for x, so like you can raise it to any power. And the range will be y is greater than 0 if a is a greater than 0 number. And if you happen to have an a value that's less than 0, which we can do it mathematically, but it won't represent necessarily a real life situation, it might be something more theoretical, then the y values would be less than 0. So we can still graph it with those numbers, and you'll see what that looks like, but it won't necessarily represent something that's tangible to us. Okay, so going on to graph. Now, the exponential function can be kind of stretched out with some extra information. You know, the more information that you have, the more specific you can make that graph, or the more detailed it would be. So we have our parent function, which is the most basic exponential function, would just be a times b to the x, right? Now that x value, if you subtracted something to it, kind of like when we're doing vertex form and quadratics, that would shift the graph horizontally. And then if there's a number at the end, that will shift it vertically. So of course, when those values are positive, it would shift them to the right or up. If those values are negative, it would shift them down or to the left. And the asymptote in those cases will move according to that k value. Okay, so a couple things we're going to do with the graph. First, we're going to just start out doing the basic graph. We're going to identify the y-intercept, the asymptote, and the domain and range. And then we'll get into some with the shifting after that. Okay, so for the first thing, we're going to graph this function. Now, basically, when we graph exponential functions, for the most part, you can use your graphing calculator to get your table of values and work off of that. You could just make your own table of values on a piece of paper, however you want to do it, but you obviously have to get some points, right? So now remember, because your x value is this exponent, I'm going to start out with my x being 0. So if I put a 0 in here, 4 to the 0 power is just going to be 1, and then 1 times 1/2 is 1/2. So we know that that's going to be that y-intercept like we had said before. And then maybe you want to put 1 or 2 positive and negative, or you could get these off your calculator like I said. So if I put in a 1, 4 to the first power is 4, half of 4 is 2. If I put in a 2, 4 to the second power is 16, and half of that is 8. Now if you did negatives, 4 to the negative 1 is 1/4, and 1/4 times 1/2 is 1/8. And if I did a negative 2, I would have 1/16 times 1/2, which is 1/32. And you can get those off of your graphing calculator without a problem. If you were going to use your graphing calculator, I would probably type in 1/2 in parentheses and then times 4 raised to x like that. And then I would just go to my table of values and get my numbers. Usually you want to get the numbers that are pretty close to 0 for your x, because those are the ones you'll be able to fit onto your graph more easily. So as you can see, 0.5, 1, 2, 2, 8, and then the negatives, you have -1 and 0.125, and then so forth. So you can kind of get an idea. So if I'm plotting this, my -2 and 1/32, or the decimal approximation, would be something very close to my x-axis. Then -1 and 1/8 would be just like a smidge higher. Then we have 0, 1/2, 1, 2, and then 2, 1, 2, 3, 4, 5, 6, 7, 8 will be just off the graph right there. So this is what our exponential growth curve would look like. Okay, so a couple things here. So I know that my a value, right? I'll write it up here actually, was 1/2. So that tells me that my y-intercept was 0, 1/2. The asymptote is x equals 0 here. We can see that, or I'm sorry, actually, y equals 0. Okay, it's this horizontal line, which is, in this case, the x-axis. And you can also get that by identifying your k. So you'll notice that since there's nothing adding to the end of that equation, so like my k value here, there was no k value for these first two, there is no k. So we know right away the asymptote is going to be y equals 0. Okay, so let's take a look at the next one. So the next one, you can use the chart if you'd like, or on your calculator to get these points here. And I'm just going to kind of write down what I get on my chart. So I know when I put a 0 in, I'm going to get a -1. And then I have -1 and 2/5, or the decimal approximation for that, -2, and then I have -4/9. If I use a positive one, I have -1.5 or -3/2, and a positive 2, I have -9/4, which is 2.25. So when I go to plot these, -2 and -4/9, -1 and -2/5, then 0, -1, 1, -3/2, and then 2, -2.25. So, oh wait, hold on, those were negatives, and I plotted them above the line by accident. So that would have been here, and this one would have been here, let's say. Okay. So now, like I said, this would not be an actual like exponential growth or decay problem because there is an a value here that is negative. So while I can still graph this problem, and I know my y-intercept then would be 0, -1, my asymptote is y equals 0 again. But you see how the graph is underneath the x-axis. So that would be a starting value that's a negative, which wouldn't happen with something that's tangible like population or money or things. But the actual problem is still graphable. It's sort of like imaginary numbers. You can't necessarily see them, and they're not going to pertain to something you would handle with money or whatnot, maybe, but it doesn't mean that it doesn't exist in other theoretical applications. Okay, so now let's go to number 3. So this time my a value is 2, my h value is +2, and my k value is -1. Now the reason why I'm writing those is because some of these numbers are going to help us, right? Now this time the y-intercept is not just going to be 2, and that's because we have this shifting going on. So if we didn't have that -2, -1 there, and the graph didn't shift, then the y-intercept would be 0 too, but this graph is going to be shifted, so it won't be. Okay, so the parent function of this would just be this. And the reason why, now you have a graphing calculator, so using a parent function isn't necessarily necessary because you could just plug this whole thing into your graphing calculator, get the points on your table, plot them, and be done. But if you didn't have a graphing calculator, you would probably not want to make a table for this big thing because it's just a little more confusing. So you would just graph this parent function. So to graph this parent function, I would know if I put a 0 in there, right? And I'm going to do this like in black, let's say. I'll do my parent function in black. So I would have a 0, 2. That would be 1 point. And then let's say I put a 1 in for x, then that would be 1 and 6. And let's say I put a -1 in, then I would have 2/3. So it'd be something like this. So I'm going to just kind of do a little dotted line. So that's what the graph would look like without the -2 and the -1. But because I have that -2 and -1, that tells me I'm going to shift the graph 2 to the right and 1 down. So I could just take those points that I just plotted and shift them 2 to the right and 1 down, 2 to the right and 1 down, 2 to the right and 1 down, and then you can see that the graph is going to end up kind of like this. So it's just a way of graphing it without typing that big long thing into your calculator or making a chart for that big long function. It's much easier to make a little table for the shorter one and then just shift all your points. Notice that the asymptote here is y equals -1 because that was the k value. And if you still need to know the y-intercept, we know the y-intercept of the parent function is 0, 2, but what do we end up with when we shift it? Well, that's where you really do have to just put the 0 into the original function with everything in there. So if I was going to do that, I would have to put in 2 times 3 raised to 0 minus 2, so it would just be negative 2. And then, let's see, was that a minus 1? And then hit equals, and I'll get that number there, negative 0.7 repeating, which kind of looks like that's where it could be. And that's pretty much it. That's how you're going to find all that information. So let's review some more of these graphs where we can actually do this shifting and get kind of used to like how all the numbers affect where things are on the graph. Okay, so looking at these first couple. Now this one's a nice parent function formation. So I don't have to worry about doing a parent function and shifting it. So I'm going to just go right to identifying my A, which is 3, and my H and my K are both zeros in this problem. So we're not going to have to shift anything. So I'm just going to go ahead and get my table of values, and it's quicker for me to just kind of do it like this versus flipping back and forth, but you're more than welcome to use your calculator to get this. So if I put in my 0, since that will be my y-intercept, I'm going to get a 3. If I put in a 1, I get 6. If I put in a 2, I get 12. And then if I put in a negative 1, I get 3 over 2, or 1.5. If I put in negative 2, I get 3/4, or 0.75. So now I'm going to graph this, negative 2 and 3/4, negative 1 and 1.5, 0, 3, 1, 6, and then that's all that I can really fit. Okay, so now we want to fill in this information underneath the graph. And the cool thing is you can really fill it all out before you even do the graph. So we know the y-intercept here is if you plug in that 0, you got 3. So that's pretty straightforward. Just plug a 0 in for x and whatever you get. The domain, if you remember from the notes, is always all real numbers. And we do this fancy R symbol for all real numbers. Your asymptote is just always going to be y equals whatever the k value is, which we already knew was 0. And then your range is going to be y is either greater than or less than the k value. Now, if you look at your graph, if you've already done your graph, you could see the graph is all above your asymptote. So you know the y values are all greater than. But the other way you can know that is just by looking at your a value. Whenever the a value is positive, you know it's going to be above, so your y will be greater. So let's try filling that information in for the next problem without actually doing the graph first. So if I go to the next one, again, I have a nice parent function here. There's no h and k. So the first thing I like to do is say, okay, what's my a? It's 1/4. H and k are both 0 in this situation. So right away, since I do not have an h and a k, I know that the y-intercept is 0 and my a value. So this is going to be 0 and 1/4. I also know my asymptote is going to be y equals 0 because that was my k value. And the range is going to be y is greater than 0 because my a was positive. Domain is always 100% of the time for this section, all real numbers. So now I could go back and graph if I need to. I already have the 0 and the 1/4, and I already know it's going to kind of level out here, right? But I might want to find a couple more points to see how wide or narrow it is, right? So if I'm going to do some points here, you can get those off your calculator. So let's say I put in -1, then I would have a really tiny little decimal, right? I think it'd be 1/64. If I put in a +1, I would get 4. If I put in a +1, yeah, +2, I believe 16 squared. I'm not sure what that is off the top of my head. I think it's 64 that you would get there when you do the 1/4 of that. Okay, so 1 and 4, and obviously 2 and 64 is going to be way off my graph. I'm not going to be able to fit that. And then this one will be really close down here. Okay, so now let's go to the next one. One more that does not involve shifting. Okay, so again, looking at this one, it's just a parent function. There is no h or k again. So my a value is negative 2/3. My h and my k are both 0. So I don't have to worry about doing a parent function and shifting it. It's just going to be what it is. So I'm going to fill out the information underneath the graph first. Now this time, since my a value is negative 2/3, I know that my y-intercept is 0, negative 2/3. And that's because the h and the k were 0, so there was no shifting. That means my asymptote is y equals 0 because the k was 0. We know the domain is always all real numbers. Now the range this time is going to be y is less than 0 because the a value is negative. We know the graph will be underneath the x-axis, and that's why the y values will be less than 0. So now to actually put this graph on the paper, we have, again, you just get a few xy points from your calculator or from just plugging them in your head. So I already know that one. Now, if I put in a 1, 3 to the first power, that's 3, and then 3 times negative 2/3 would be negative 2. If I put in a 2, I would get 9, and negative 2/3 of 9 is negative 6. And then maybe I'll do a negative 1, which would flip that 3 to the bottom. Negative 2/3 times 1/3 would be negative 2/9. Okay, so negative 1 and negative 2/9. 0 and negative 2/3, 1 and negative 2, 2 and negative 6. Now you can see the asymptote is still y equals 0, but because the graph is underneath the asymptote, that is why the range is y is less than 0. Okay, so now we're going to do the same thing on the next 3, but this time we're going to graph our parent function, which I'm going to highlight, and then we're going to shift it according to the h and the k. Okay, so for the first one, I know my a value here is positive 4, my h is positive 1, and my k is positive 2. So I'm going to do my parent function graph first, and then I'm going to shift it. So that's why I'm doing the parent function in black. So this is the part I'm going to do in black. I'll do like a little dotted line so you can tell that it's just that part, and then we'll shift it according to that 1 and that 2. So of course, if I put a 0 into my parent function, I know the a value is my corresponding y. If I put in a 1, 2 to the first is 2, and 2 times 4 is 8. If I put in a 2, that would be 16. And then I'm going to do a negative 1, which makes it 1/2. 1/2 of 4 is 2. And then if I put in a negative 2, I get 1/4. And so 4 times 1/4 is 1. So now I'm going to graph my parent function here with a black dotted line. So negative 2 and 1, negative 1 and 2, 0, 4, 1, 8. And that's really all I can fit because the rest would run off the graph. Now, because my h was 1 and my k was 2, h being 1 is going to shift 1 to the right, and my k being 2 is going to shift 2 up. Okay, so when I go 1 to the right, 2 up for each of these points. 1 to the right, 2 up. 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 And it's going to look like this. Now this was kind of nice because the y-intercept, we can see it on the graph. It's right here, so it's actually 0, 4. The domain is always all real numbers, even if you're shifting, that's still all real numbers. The asymptote then was y equals the k value, which was 2, which makes sense. It looked like it was leveling out at the 2. And then our range is y is greater than 2 since our graph is above the asymptote or the a value is positive. Okay, so let's go ahead and try the next one. Now, before I even do the graph, let's fill out the information on the bottom this time. Okay, so we have our parent function highlighted here in yellow. and we know that the A is actually not there. You don't see the A, so it's actually a 1. The H is -2, and the K is -3. So since my H is -2, we know that the parent function is going to shift 2 to the left. Since the K value is -3, we know it's going to shift down 3. The y-intercept, of course, the K value is 3, so it's going, the asymptote's going to be y equals 3. The range will be y is greater than 3, since our A value is positive. The domain is all real numbers. Now, as far as the y-intercept is concerned, you know it's going to be 0, something. That's what a y-intercept is. So you have two options. You can just plug 0 into the entire equation and figure it out, or you can wait till you shift the graph and see if you happen to see it on your graph. So if I were to graph the parent function, which I will do in the black, so when I put the 0 into the parent function, I just get 1. If I put a 1 in, I get 7. If I put a 2 in, I get 49. And -1 is 1/7, and a -2 is 1/49. So my parent function, I'm going to do in the black dotted line. Okay, so you see the asymptote of every parent function is always at the x-axis, and it's kind of going up. So now we can use our little shifting to get the points on the actual graph. So we're shifting them each 2 to the left and 3 down. So 2 to the left and 3 down. 2 to the left and 1, 2, 3 down. This one, 2 to the left and 1, 2, 3 down. And this one, to the left and 1, 2, 3 down. So you can see that it's starting to level out at this K equals -3. And it'll be something like that, right? So now I can't see what my y-intercept is on this graph because it's going to cross through way up here somewhere off the graph. So then I can just put this in on my calculator and substitute in that 0. So I'm going to do 7 raised, and 0 plus 2 will just be 2. Whoops. Try that again. 7 raised to 2 minus 3, and I get 46. So obviously that's why I couldn't see that, because it's going to cross through at 0, 46. So if you can't see that intercept on the graph, you will have to plug at least the 0 in, or you could have typed the whole thing in and gotten it off your chart on the table of values if you're using graphing calculator. Okay, so our final one here. So we do have a negative A value this time, so it's not exponential growth or decay. It's in a graph underneath. Our H value is going to be -4. It's always the opposite of the sign you see, and K is going to be +1. So we know this graph is going to shift 4 to the left and 1 up. So shift 4 to the left and 1 up. Domain still all real numbers no matter what. The asymptote is y equals that K value, which in this case is 1, and the range will be y is less than 1 because we have that negative A value. Our intercept will be 0, whatever we get when we plug in the 0. Okay, so to go through and do the actual table of values, I'm going to do my parent function because that's a little bit easier for me to figure out in my head. Now, even if you're graphing these with your calculator and you're putting the whole thing in, that's fine. But I will have questions on the quiz that ask you about the shifting and stuff. So just make sure you understand that. Okay, so putting in the 0 to my parent function would give me a -2. Putting in a 1 just to this parent function here would give me -6. And putting in a 2 to my parent function would give me a -18. If I put in a -1 to my parent function, I would get -2/3. And if I put in a -2, I would get -2/9. So I'm going to graph my parent function with the black and do like a dotted line so I don't get confused on what I'm doing. So -2 and -2/9 will be right around there. -1 and -2/3. 0, -2, 1, and -6. And that's pretty much all I can fit. So this is what my parent function will look like. Now, if I'm going to do my shifting now, I'm going to shift each of these points, 4 to the left and 1 up. So 1, 2, 3, 4, 1 up. Oops, still in the wrong color here. Then do this one, 1, 2, 3, 4, 1 up. Then this one, 1, 2, 3, 4, 1 up. And my last one, 1, 2, 3, 4, 1 up. Okay, so once again, I can't really see what that y-intercept is from the graph because by the time it crosses that, it's going to be way down here. So I'm going to use my calculator to help me find out that y-intercept. So I'm going to have -2 times 3 raised to 4, because 0 plus 4 is 4, obviously, and then plus 1. And I get -161, which obviously I would not be able to see on that graph. All right, so hopefully that answers any questions you might have on the graphing itself. Okay, so we can understand how to identify the y-intercept, the asymptote, the domain, the range, and you understand how that h and k value shifts your parent function, either left, right, up, or down. Okay, so now to identify the y-intercept and the asymptote of the function. So remember, the asymptote is just y equals the k value. The y-intercept is usually 0 and the a value, but that's only when the h and the k are both 0. If they're not 0, you're just going to have to plug in the 0 and get that. So for this one here, to find my y-intercept, I'm just going to plug in the 0. So then it's really 4 raised to -3. And then 4 raised to -3 is really 1/64, or the decimal. The asymptote is just y equals, in this case, 0, because the k is 0. Okay, so for number 2, the y-intercept is going to be 0, comma, whatever you get when you plug that 0 in. So 10 raised to 0 is just 1. 1 times 1/5 is 1/5, but 1/5 minus 2 is -9/5, or you might have -1 4/5 or -1.8, it's all the same thing. And then your asymptote is y equals -2, because that's the k value. Okay, and then the third example here, your y-intercept is whatever you get when you plug in 0. So if I plug in 0, I have 8 to the -1, which is really 1/8. 1/8 times -1/3 is -1/24 plus 3, which would give me 21/24. Then the asymptote is just simply y equals whatever that k value is, which in this case is y equals 3. Okay, domain and range, just a little practice with the domain and range. We know that for every single one of these exponential functions, the domain is always all real numbers. So you can just go ahead and write that for all 3 of them. That does not change. Then our range is going to be y, right? The k value, and if the a is positive, it's greater than the k value. If the a is negative, it's y is negative or less than the k value. So for this one here, our a value is 1, so it's y is greater than 5. Okay, so just a couple real life type of problems with these percentages and whatnot where we use these exponential models. So when a real-life quantity increases by a fixed percent each year, the amount y of the quantity after t years can be modeled by the following equation. So A would be your initial amount. So like I mentioned to you earlier in the lesson, it is what you are starting with. The R is the percent increase expressed as a decimal. So if you have like 15%, it's going to be 0.15 or whatnot. And 1 plus r would be called that growth factor. So remember that b value. So we were talking about a times b raised to that exponent earlier. This 1 plus r is the same thing as your b, and that's called your growth factor. And if you remember, we said that the b had to be greater than 1. And if you're adding a percentage to a 1, it should be greater than 1, so it shouldn't be a problem. Okay, so in 1990, the cost of tuition at a state university was $4,300. So A equals $4,300. That's our initial or starting amount of money. Then over the next 8 years, the tuition rose 4% each year. So that R, that rate is 0.04. So writing a model that gives the tuition in dollars T years after 1990. Now, oftentimes the T, if it's representing time, that's really the X value. So on your calculator, you're going to use X, but it's representing time in these types of problems. So the model, you're still going to have your Y. You're going to substitute in just the A value, which is the 4,300, and then 1 plus 0.04. And raise that to t or x. I don't care which variable you use. Now, a lot of times at this point, this is your growth rate, 1 plus your growth rate. So you can actually simplify that part to your growth factor. Your growth factor is just what you get when you add the two together, and it should be a number greater than 1, which if you're adding 1 to something, it should be. And so this is your model here. So now you can use that model to figure out how much it's going to be after any number of years, right? So if 1990 is like your year 0, 91 would be 1 year, 92 would be 2, and so on. So 96, you're going to use t equals 6 to solve that. So on your calculator, you're going to do 4,300 times 1.04 raised to 6. And there's 2 ways you can do this on your calculator. So the first way is to just put it in like the normal screen, right? So we have 4,300 times 1.04 raised to 6 like that, and you get your answer, which is 5,440 and 87 cents. Now, if you had to calculate this for multiple different years, let's say it asked you for tuition in 96, 98, and 2000 or something like that, and you don't want to have to keep calculating the problem multiple times, you can use your y equals instead. Type it in there, 4,300 times 1.04, but instead of raising it to a number, you're going to raise it to that x. And you'll notice on your variable button on the graphing calculator has an x or a t. So that's why you have to put that there. So then you go to your graph, you see what it looks like, but go to your table. Come on, second graph, get our table. Okay, so now obviously time can't be less than 0. So at 0, we had 4,300. If we go to 6 years later, which was the 1996, we see our number, 5,440, and they just rounded it to 90 cents. And if you needed to go the next year or, any amount of years after that, you can just keep going through your table and getting all the answers. So when you need more than just 1 year's amount, it's a good option to give you all of the different years in one shot. Okay, and then let's finish up our last portion here. People often confuse percent increase and growth factor. So like I just showed you on the last slide, percent increase is just the percent, but the growth factor is 1 plus that. So it increases it by 100%. A percent increase of 200% means that a quantity tripled because the growth factor would be 1 plus 2, because remember, 200% is really 2, and when you add it to the 1, your growth factor is then 3, so it's actually tripling. So if you double something, you've increased it by 100%. If you've tripled it, you've increased it by 200%. And sometimes people get confused on that, so it's a good point worth noting. And then finally, we have compound interest, which should be kind of interesting for everybody because it's something that deals with money. So compound interest is interest paid on an initial investment or a principal and previously earned interest. So let's say you invest $500, first month you make $5 of interest. Well, now the next month you're getting interest on $505. So your interest is accruing more. And that's obviously the whole point of investing. So this formula here, you want to just plug everything in and work it out. Now, the A is the amount that we're solving for, like how much do you have in 10 years or whatnot. The T is obviously the time. This P stands for that initial balance of money you're putting in. So I want to invest $500 or something like that. The R is the rate, written as a decimal, whatever that interest rate is. The N is going to be how often it's compounded. So the basic formula that we already did had to do with things happening yearly. So that basic formula on the previous page, this one here, the A times 1 plus R raised to T, that's when things are happening on an annual basis. Now, compound interest, sometimes your interest is applied quarterly or monthly or daily, like credit cards and different things. They do it all different ways. So you have to consider that. The more frequently the interest is being applied, the more that balance is going to go up. So if it's money that you're investing, that's a good thing. But if it's a credit card that you're paying and the interest is accruing daily, that's not a good thing. So it just depends on the situation. So these are different periods. So just make note of this in case you get a problem and you want to know what it is. Annually would be 1 time per year. Semi-annual would be twice or 2 times for the end value. Quarterly would be 4. Monthly is 12. Obviously, there's 12 months a year. And daily, we'll just go for 365. So for example, if you deposit $1,500 in your account, that's going to be that principal. And your account is going to earn 6% annual interest. So that means your R is going to be the 0.06. Find the balance after 1 year. So that's going to be the T. And then you're giving these various N values, depending on how it's compound. So if it's annual, your N will be 1. So to find this problem, we're going to substitute in the 1,500. And then we're going to do 1 plus the rate over that N value. And then out here, it's going to be the N value times 1, which is obviously just 1. Now, when you put this in your calculator, be very, very careful. Because sometimes I recommend you do pieces at a time. So what I would do for this one, you all probably know what 1 times 1 is, right? So we don't need to worry about that. So just do the part in the parentheses and save yourself trouble. Otherwise, you're going to need a whole bunch. So all you're doing in the parentheses right now is 1 plus 0.06. You can all do that, right? You probably already knew is 1.06. Now you're raising it to the exponent, which we know is 1 times 1, which is 1. So if I raise that to 1, it's not going to change anything. Now I'm going to multiply that to the number out front, which is that 1,500. And I get 1,590. Okay, so that's going to be 1,590. So that's how much money I'm going to have after 1 year if it's going to be done on an annual basis. All right, so let's try semi-annually. So this time I'm still having my same initial investment of $1,500. But this time I'm going to have the same rate of 6%, but this time I'm going to have it added on twice in the year. And then my exponent here is going to be 2 times 1. So what I would advise you to do is just do the parentheses on your calculator. So 1 plus, and actually I always started with the other part first. So I go 0.06 divided by 2 plus 1 and have 1.03, right? So now you can just keep that on your screen, raise it to the second power, and then multiply that to the 1,500. And we have 1,591.35. So you can see you get like a smidge more money because that interest was applied twice, not just once in the year. All right, so let's try it for 2 more. So for number 3, we're going to do the same thing, but this time we're going to do it quarterly, which means our N will be 4. So we're still using that 1,500. 1 plus 0.06, but this time it's going to be divided by 4. And then we have 4 times in the year, so it's 4 times 1. And then again, just putting that all in on your calculator. So I would probably start out with the parentheses, so 0.06 divided by 4, add the 1. Now you got what's in your parentheses, raise it to your exponent. 4 times 1 is 4. Then multiply that to your initial investment out front. And we've got $15.92 and 5 cents. $15.92 and 5 cents. And then finally, we're going to do this for a daily. When it's daily, that would be 365 times. So 1,500 times 1 plus 0.06 over 365. And then that's 365 times 1. And we're going to put that in our calculator. So 0.06 divided by 365 plus 1, that's our parentheses. Raise it to 365, and then multiply that to the 1,500 out front. And we have 1592.75. 1592.75. Now, obviously, the more often your interest is applied, the more money you're going to make. But this was only for 1 year. So imagine how that might have an impact over 10 years or over 20 years. The higher the interest rate, yes, but also how often is that applied. Okay, so that is it for our lesson today on exponential growth. It was a little bit on the longer side, went through a lot of information. Tomorrow we will do exponential decay, which is going to be a lot of the same thing again. So even if some of this was a little unclear, when we go through the decay tomorrow, it's going to be pretty much the same, just that that B, or that growth factor, will now be less than 1, will become a decay factor. But the process for doing the graphs and all that kind of stuff is the same. So it'll be a good review as well. And just don't be afraid to reach out if you have any questions. Have a great rest of your day.